ahead and
Cool. All right, I see attendees are already trickling in. 8, 9, 10. Awesome. Welcome everyone who's joining us this morning or afternoon or evening, depending on where you're located. Thank you all for participating in this event today. We're really excited to have you here. I'm going to kick it off. My name is Isabel McCann. I work at the National Renewable Energy Laboratory, and I am the communications lead for the Global Power System Transformation Consortium, which is the host organization of the webinar today. I'm going to hit a couple event housekeeping items here real quick before we get started. So the event is being recorded and will be shared with attendees on, yes, okay, we are recording already. So the event is being recorded and will be shared with attendees. As you're joining, everyone's will remain muted upon joining and throughout our presentations. This is in broadcast mode, so you are all muted. However, we want it to be really participatory and we want to really engage with you guys today. So please use the chat function, specifically labeled chat, in your Zoom toolbar. Feel free to introduce yourself there, and throughout these presentations, if you have comments, feel free to use the chat specifically for comments or specifically to introduce yourself. If you have questions, like I said, we want this to be really participatory and engaging. We have a Q&A session scheduled for the last 10 minutes or so of this event, but we would like you to put your questions into the Q&A function. It is distinct from the chat function. The Q&A function allows us to better organize and see your questions and address them as they come up, and then address them in our Q&A session at the end. So take a look for that Q&A in your toolbar, that Q&A function in your toolbar, and you can feel free to submit questions on a rolling basis. Submit them as they come to mind throughout the presentations, and like I said, Barbara, our moderator, at the end, we'll have a moderated session. She'll take your questions and present them to our speakers today. If you have technical issues, please use the chat feature to message Lady Maya Kane specifically. She's our technical coordinator today, and if you're having any tech issues, she can help you troubleshoot. You can adjust your audio through the audio settings. If you're having any issues, you can also dial in and listen by phone. All of that information can be found in your registration confirmation email. You can also always visit the Zoom, help desk, and there's a lot of good troubleshooting there as well if you have any technical issues. Finally, I want to flag that we will have a survey that launches at the end of the event as soon as we conclude. Please take a moment to fill out that survey and share your feedback with us. It's really helpful for us just to kind of understand how these go, how we can improve, what went well, what questions you might have, things like that. So with that, I'm going to take a moment and just introduce today's speakers. So our moderator for this event is another team member from the National Renewable Energy Laboratory, Barbara O'Neill. She is also one of our country leads for the Global Power System Transformation Consortium. One of our technical presenters today is Xuan Dong, who is also an analyst here at the National Renewable Energy Laboratory, and we'll have one of our presentations. And then last but not least, Nick Miller, the principal at Hickory Ledge LLC, will be presenting on the Oscillations Guide, and again, we'll be sharing another presentation today. So with that, I am going to hand it over to Barbara to cover a couple introductory slides. Barbara, feel free to take it away and just cue me as you want me to progress the slides. Thanks, everyone.
Great, thanks. Thanks, Isabel. Okay, so just to reiterate, go ahead and introduce yourself in the chat as people are coming on, and questions will go in the Q&A, the separate icon there. Okay, hi guys, Barbara O'Neill here. I've been with National Renewable Energy Laboratory for about 11 years, working in the grid integration space, mostly working on the international front, trying to help various jurisdictions around the world increase wind and solar energy, basically. Now batteries as well, but how do we up the ante for inverter-based resources? Next slide. So I just want to provide some context for why we're here, because it's astounding to me. We hear about the leaders in this space. We hear about some of our founding system operators, excuse me. And we're like, wow, these jurisdictions, these ISOs are so progressive. They're doing amazing things. I mean, we look to Ireland a lot with respect to being an islanded community with, how they're really pushing the envelope with high wind. We look to what AMO's doing in Australia. It's fabulous. The US, UK, et cetera. And then you look at this graph. In order to get to our 100% by 2050 goal, which will still, sort of push us toward that 2 degrees Celsius decrease that we're going for in terms of global warming and decarbonization, we still are this far from it. So if you look at the 2030 IEA, International Energy Agency target, we're still sort of that far below it in the progressive countries. So what about all these other countries who are struggling, who don't have the infrastructure and the systems in place to really take on modifying their system? And what we want to say is that there's a way to leapfrog. There's a way to learn from the peers, the other system operators out there who are doing great things. Um, Oscillatory events are happening more and more with higher IBRs, and we're here to learn about that and talk about how you can look at that, how you can analyze that. Next slide. So the fact is that as we bring on these renewables, we really need to keep an eye for the reliability and stability that we're used to or that we aspire to. And trust me, there's systems that I work with that say, okay, we don't have the luxury of looking at wind and solar because our system isn't solid enough right now. And I say, this is like the wrong attitude, right? We need to realize that because of the speed and the performance of power electronics, because of the programming and the control algorithms, because of the capabilities with grid forming inverters, we can we can really utilize the features, and we need to just do that in a way that makes sense, that's coordinated. So this slide highlights some of the areas that we need to work on. We definitely want to share all those lessons among participants in this arena. And I mean system operator, I mean equipment manufacturers, I mean research institutes and think tanks. Let's figure out where the new tools and methodologies and research areas are that we should focus on. Next slide. So G-PST was formed, and probably most of you know who we are, but just to kind of go over it, the logos are really tiny, so get on your magnifying glasses. But with a variety of organizations that had gotten together and collaborated over the years on certain projects, but went, okay, let's come together in a more formal structure of sharing our experiences and sharing our research and making sure we all have the latest and greatest innovation, tools, knowledge. Like, let's put that together and let's really break down those silos to enable this research to go forward and leverage what we're all doing. Let's figure out how to develop the next era of methodologies to deal with a very different system. That whole paradigm shift of the utility arena is really happening. I see it, and it's very exciting, but there's a lot of lessons to get past. And so with G-PST, we look at peer exchanges, we look at these webinar sessions, we look at specific technical assistance, we look at understanding how to take what we've learned with IEEE and FERC standards, as well as IEC, and kind of localize them or customize them to various jurisdictions. So I've worked around the world with a whole spectrum of sophistication and sizes of systems, and they're all able to take on more renewables. Like, I see the opportunity there, and I see it as an opportunity too for their community, for their workforce, and that kind of thing. Because as we transition to clean energy, I think the benefits do really ripple throughout. Next slide. So some of the things that we've done in the space, these are just examples. You can read them on your own, but sort of cut across these 5 pillars that we've set up. So there's the research pillar where we dig really deep into saying, what is next? What is the next thing we should all drive our attention toward and share knowledge on? And then with the technical support, it's a bit more customized to the jurisdictions as I've described. With workforce development, we've got the new latest and greatest curriculum. Imperial College is leading that pillar. And we have a great Women in Power System Transformation program where we share interns across the globe and really kind of develop networks and learn from each other in that sense. That localized technology adoption has a lot to do with standards and codes and how to get that grid code up to sort of a modernized, a more appropriate view with increased IBRs. And then what data and tools are open available, what's open source, and how can we all contribute to improvement of that code on GitHub. And with that, I'm going to pass it to Nick Miller. Nick, if you want to do your own brief introduction, and appreciate the time. And you're muted.
After all these years, you'd think I'd know not to mute, huh? Okay, it's a great pleasure for me to be here, and I'm so excited to have people from so many parts of the world on the call. I love to travel, and I've worked all over the world on renewable integration for many decades. I recognize a lot of names on the attendees here, so hi to all my friends, and hello to everybody that's new to me. Just as a word of sort of background on myself, so I've been working in power system dynamics for many decades, and I worked for General Electric for a big chunk of the century, including on controls and dynamics for wind and inverter-based resources. So today I'm going to give you a quick introduction to a new document that I led through Energy Systems Integration Group, ESIG. So ESIG and G-PST are connected. ESIG is the leader for one of the pillars of G-PST, and the topic of oscillations in power systems is of tremendous interest. Obviously, the reason why we got such good attendance today. So this is introduction to a new document that is a practical guide to the diagnosis and mitigation of observed oscillations in IBR-dominant systems. So this is born of a document born of concern raised by founding members of G-PST that oscillations are happening. What do we do about them? And particularly from the point of view of something practical. So many of you on this call I know are from operating utilities around the world, and the intent of this guide is when somebody is a system operator is in the line of fire and you observe, you get measurements of oscillations occurring, or you observe oscillations also in system simulations. The question is, what is going on? So this is, and the answer for those of you that are in the line of fire is not practically here's 1,000 IEEE and SIGRE papers, go figure it out. So what we've attempted to do is to make a guidebook, and I have a little graphic here on this slide that sort of gives you the gestalt, if you will, of the guide. This is the first line of defense, and we already have system operators around the world that have hard copy. The idea is that this is a document that's sitting on your desk or on the shelf. You see an oscillation, this document is going to be used and dog-eared and have coffee stains on it. It is not intended to tell you everything you could possibly want to know about oscillations. It's a place to start and try to develop an understanding of what might be happening, how to go from might be happening to actually this is it, and what you might do about it, and how to continue. So this entire document is about 150 pages out of a population of tens of thousands, hundreds of thousands of pages of published material on oscillations in power systems. So we go at this thing as though, and I use the word diagnostician often in the guide, it's your responsibility to go figure out what it is. You're the doctor, somebody's sick, the system is sick. So think of it that way. So to start things off, there's an executive summary, which I would encourage everybody to try to read. You don't need to be somebody that's down in the weeds to sort of get the introductory discussion. So the document is laid out in progressive depth. So those of you that are on the call that are sort of, what are oscillations? Why should I care? Without being charged with fixing them, can learn from reading the executive summary and from reading the first 20 to 30 pages of foundational system stability discussion that will help you get grounded in what's going on. This is from the executive summary, and this is, again, emphasis on practical, right? There's lots of stuff about eigenvalues and simulations and all this esoterica, but we're trying to be practical here. And there's three fundamental truths that are emerging about what's driving oscillations most of the time in high IBR systems. And the first one is something's busted. All right, something was implemented in a fashion that you didn't expect. Something is not working, whatever. Those classes of problems don't lend themselves immediately to diagnosis with simulations until you figure out what is physically different from what your model said it was. The second common problem that we see recurring all around the globe is that the controls, IBRs have the ability to be incredibly aggressive, very fast, very high gains, very fast responses, and those can create stability problems, particularly oscillatory problems. So the idea that faster is better is absolutely generally not true. The mentality should be what is fast enough. And controls that are too aggressive drive oscillations, and that's one of the first places you look after you determine that the system isn't actually broken. And then the third one is that you've done something wrong in the simulation. And there's many, many places that you can go wrong. So the guide has a lot of kind of wisdom, practical wisdom, that you won't find necessarily in academic work that tells you where to look. We have introduced a taxonomy of oscillations. Many on the call will recognize this IEEE taxonomy of system stability on the left. I'm not going to spend a lot of time with it, but many of you will recognize that. That taxonomy, and there's a similar one from Seagray, is very useful for a broad picture of system stability, but it's not all that. It doesn't lend itself well to diagnosis of oscillations. So we have a slightly different taxonomy, 5 classes of causality. So we're going into this as like, what is causing the oscillations? And those are listed on the right. There's 5 major categories and 15 subcategories within the guide. I can't go through all of them. And then the guide is laid out in this process that's captured by this flow chart. And there's a lot of supporting, but there's a rhythm of diagnosis. I see an oscillation. If I see it, if I being you, user, if you see it from a field measurement, something that showed up in the operating room or something that showed up in oscillography from a relay or something like that, you kind of know it's real. That's on the left side of the top of this taxonomy or this flow chart here. If you see it in a simulation, okay, the diagnosis and fix for oscillations that occur in simulations are quite similar, but there's a very important step that's shown in orange here, and that is, do you believe the simulation before you run off and try to fix a problem? And there's a lot of guidance in the guide as to how to determine whether or not you really believe your simulation before you go off and try to fix it. And then the next major block is this initial assessment. What is it? What might be sick with the patient? Huh? And there's a bunch of tools. I'm going to introduce you really quickly to sort of the framework of that. And then you come out and say, oh, I think it is torsional subsynchronous oscillation. That's one of those 15 to 20, and then you dive into a more detailed assessment. To help the reader, there's a hierarchy within the guide that goes deeper and deeper. And again, remember, this is not all things, all oscillations. This is practical, most likely. And then we go in to try to figure out what's causing it and what you might do about it, whether you need to do something about it, and what your options might be, from simple to complicated, from cheap to expensive. So this is an overall flow that is replicated throughout the guide. So what do you do? What are your tools at hand? And then later in this lecture, Schwan is going to take you through some of these tools. This is for lack of a better word, a shopping list of the tools that are reviewed in the guide. There's a page or two of discussion of each of these. So those of you that are more familiar and are living in this space will understand that a discussion of state space methods isn't accomplished in 2 pages. It could be a lifetime of study, but these are introduction, how you might use them, what the results might be useful for, what kind of options you have, and then we have a very generous reference section where you can dig deeper. So Schwan is going to use a couple of these bullets in his example, and that will help you get a handle on how they might be used in a particular pathology. There's a very rich space, and it gets overwhelming for practitioners. There's dozens of tools, and there are all these different things, and which is the right one? We try to give some help to the user, to the person charged with doing something practical. What tools do you pull out first for what kind of problems? And there's a bunch of guidance for that. So here's just a one-page example, very quickly. Um, two of the tools on the left are dynamic frequency scan. This is some good work from NREL, from Schwan's colleagues on the left, that talk about that look into the dynamics and frequency domain. This is an example of something that's got a 17 hertz poor behavior in one of the sequence domains. So those are the places you can learn things. On the right is a cool example of some of the online tools that are designed to help diagnose. So remember, my first thing in Occam's razor there is that something is broken. Well, there's a suite of tools for operating centers and for post-processing that are designed to find out where the bad actor is. Right? So the system is oscillating a lot of times. There is one resource, one wind farm, one battery, one solar farm that has got something wrong. And the question for a system operator, first question is, where do I look? And there's some great tools that are discussed. Some of these things are based on, this is an example of something that's based on PMUs that has proven to be very effective. And there's a lot of different variations on these tools coming out, but the sort of thing as I said, we got people on the call from all over the world. These are showing up in national or system level operations that will help you find what's misbehaving. Super important in oscillatory diagnostics. So this is an eye chart. I don't expect you to process everything here, but this is in this initial assessment part of the guide. And what you're seeing down the left are characteristics. There's pages of diagnostic questions, just like you'd get at the doctor. What hurts? What does it look like? What is oscillating? What does the oscillation shape look like? What condition was the grid in when it was observed to be oscillating? And then the rows across the top are the groups of causality. What's wrong with the patient? And this color coding is if you see a high intersection of yes answers to the questions with a causality, that points you in a direction of saying this is something that I need to look more carefully in. Again, I don't want you to try to process this while I'm on something, but this is an attempt to sort of collect the institutional memory into something on one page. Of course, there's huge compromises associated with this level of simplification, but the reds can be very valuable. If you see this, it is not that, is a really useful diagnostic tool. So there's a bunch of that sort of stuff. You come out of these steps and go into, okay, I think it is, I'm just using as an example, a subsynchronous torsional interaction between an IBR and a synchronous generator. All right, I've got measurements. How do I extract information from those measurements to help me do diagnostics? And then from that, what kind of additional tests? Do I go out and take measurements in the field? Do I set up computer simulations that are designed to diagnose what I've observed? All right, and there's a whole bunch of guidance in the guide for helping you set up diagnostics to figure out whether or not your guess is right, and then some checks to see whether or not you really believe your diagnosis, and if so, and this is something that system operators around the world made a big deal out of, and it's important. It's like, do I really need to do anything? Is this oscillation of sufficient of characteristic that means I, the system operator or the system owner or the resource owner, really need to fix? Because sometimes the answer is, nah, ignore it. It's not important. And then sometimes the answer is, yeah, I got to fix it. And then there's sections on how to design. A lot of times, by the time you've figured out what the ailment is, it's fairly clear what the fix is, but not always. And that may require additional simulation, additional field tests, other kinds of things for all the different pathologies. So there's guidance on this throughout the document. Here's an example that I just picked out. This is one of the 15 different pathologies. Here's a case that I think is kind of cool in that it's a voltage control induced oscillation that's linked to system stress. So this is over a course of a couple hours. This is real field measurements from a system, I think, in the United States. Although it's not important. It says in the guide, this example is explained, where you see the blue line, the loading is going up and up and up, and at some point about an hour and a half into this time sequence, the system starts to go unstable, and it finally goes so unstable after about 2 hours at 6,000 seconds that things trip. Turned out that this is a voltage control mistuning that was interacting with the rest of the system. Seeing the relationship between the system stress is very helpful in this particular case. And there's lots of examples like this. So, and then finally, not finally, again, this is a quick introduction to the guide. There are other things that I haven't put up in today's presentation. There are discussions that cut across the different 15 pathologies that are centered on, is it a forced oscillation or is it a natural oscillation? That is there some control pathology like a limit cycle or something that is driving the system at a specific frequency? Or is this the confluence of all the system dynamics that is creating sort of an unstable eigenvalue? And there's a spectrum in between, and these things talk about that. Another topic, latency, is discussed at some length, because the time it takes to go from a measurement to action by control is full of practical headaches that frequently are poorly understood and poorly modeled. And it's a recurring theme around the world that latency in controls is driving system oscillations, and it's so important. There's a whole section in here on that, and then a bunch of things about how to extract information from signals, how to set up diagnostic simulations, how to determine, as I said, do you trust your simulations? Lots of sanity checks. If you see this, your simulation is garbage. Very useful practical stuff that you won't find in academic papers. These are common mistakes, and nobody writes about mistakes of failure to pre-unitize a gain properly, or failure to go from 3-phase to 1-phase, or polarities wrong, things like that. Then there's a long section on references and some things. And one last point here is that the eSig landing page, which is in the, all right, so the document is in this orange square up to the right. We're going to share these slides with everybody, so you don't have to remember them, but if you want to capture that, it's in the eSig, on the eSig website. There's mechanisms on the landing page to give you access to get hard copy. That's a question of preference. I led this thing with the idea that it would be something that would be beneficial to have in hard copy, so that you practicing engineers on this call could sit there and learn and write in the margins. I saw this. Oh, this is important. This is relevant to my system, and learn from that. This is practical. This is I say it over and over again because the industry been hungry for practical stuff that isn't overwhelming, and that's the philosophy of the document. So I think I kept on time, everybody, and I'll accept some questions on this after Schwan goes. So I'm going to stop sharing now. All right.
That was perfect, Nick. Thank you. Also, just let people know that Nick did review this guide on an eSig webinar, and that webinar is available too on its website for free, the recording. I think on that one, you have a bit more time, right, Nick? You went into a little
That's
bit more
right.
detail.
Right. There's that webinar is about 45 minutes long and just goes a little bit deeper. That's right.
Yeah, so you'll have access to this recording as well as you can get that on the eSig site and the guide itself. We put a link to the guide in the chat section. So, okay, Siobhan, want to take it away?
Yeah, let me share my screen.
And do a intro for yourself, please.
You see my screen?
Yep.
Oh, great. Hi, all right. Thank you for joining. And this is Sean. I'm a researcher at National Renewable Energy Laboratory, and my focus is on the modeling, simulation, and stability analysis of power systems with high penetration of renewables. And as Nick mentioned, so currently we have the urgent need to solve these real-world oscillation events. And here we will let's treat ourselves as a daughter, and see one real-world problem and see how we address it. So as a background, so we agree that currently, so the IEEE definition, we introduced a new problem related to the increasing penetration of renewables, and also around the world, we see different oscillation events. So you can see in China, in AMO, in ERCOT, and everywhere in the world, especially those places with high penetration of renewables and a vehicle grid. And then let's focus on one problem, like we are doing math. So, so we have different tool case. We have different categories of the problem. So maybe one helpful experience is let's just do one problem and see how we address it. So this event happened in a system called System A, and it occurred 3 years ago. And on the left-hand side, so we have a illustrative diagram for the system. So it's a large system, and one part is here we use this blue block to show the main grid, and the detailed part that we show here include some renewables. There are a lot of renewables which is labeled by these circular shapes. And there are some bars, and this pink bars is actually some long transmission line with high voltage level. And the red region here is some region connected to the main grid through this channel. And what happened then? So there was one two-phase two-ground fault near this plant 7, and then line 1 and line 2 are tripped to isolate this fault. And following that, we see some low frequency oscillation throughout this region. And here for this line 3, due to the oscillation, line 3 is tripped. And this line 3 is connecting this red region to the main grid. So the critical consequence is that this oscillation causes the islanding operation of this red region. And that's why we are so concerned about this oscillation. And the next, so our study is purely phasor domain simulation based. And first, since the phasor domain simulation model is probably readily available there, so we quickly give a try with the phasor domain simulation, and we found that we can indeed recreate some oscillations there. And these are the voltages and the frequencies, and we add that fault, and we follow the sequence to clear the fault, and we see these sustaining oscillations in both voltage and the frequency. So two observations here. First, if we do the FFT analysis, we will see that we get some 1.5 or 1.5 Hertz oscillations here in both the voltage and the frequency. And the second issue is that if we really examine these waveforms, we see that there are some buses with minimum oscillation or no oscillation, and there are some buses with large magnitude oscillation comparatively there. And this gives us the second observation. So this oscillation events is a local oscillation events. This makes sense in large-scale power system. So some region is oscillating, some region is not. And after replaying the event, so we, as Nick mentioned, so we want to know which plant or which other components is a bad actor. So here we use one method called the dissipating energy flow method. So a little bit of background. So last century, we have a lot of study on the in conventional power system. There have been a lot of study on the transient stability, and one method is the energy function. So there have been a lot of efforts to construct the energy function, and following one way of constructing the energy function, we get this nice expression, which is some energy integral, and this integral later is used to do the oscillation source analysis. So we compute this integral and check the plant, for example, plant I is injecting energy or absorbing energy from the system. If it's injecting energy to the system, and then this method tells us that plant is a bad actor in the oscillation event. And let's see one example. So for this event, so basically we use this expression, we use the simulation resource as the input, and we do the computation. And here is what we have. So the upper part is related to P and frequency, and the lower part is related to voltage and reactive power energy, reactive power. And if we check the upper figure, we will see that these plants, they are all absorbing energy. Look, and there is a few plants to inject energy, but the slope is not so high. But if we check the voltage and the reactive part of this line integral, we will see that, for example, plant 1 in red, plant 2 in blue, these plants are injecting energy to the system. So this gives us one impression that we probably have a voltage oscillation event there, and these plant 1, plant 2, plant 3, they are the bad actors in this event. And this is our initial conclusion. And the second is one key point. So when we see the oscillation event, so we care a lot about the oscillation magnitude. And if we see large magnitude, we are nervous. But when we are actually doing the oscillation event analysis, phase angle is also one quantity that we care about. And if we just check the oscillation magnitude, so it may not tell us the correct information. So here we have an example. So the red trace, so we plot the voltage and the frequency of 2 plants here. So the red, actually 2 buses here, the red trace is corresponding to plant 1, which is the major oscillation source based on the dissipating energy flow method that we on our last page. But if we plot the voltage and the frequency at another bus around here, which is the bus 10 here, we will see that the bus 10 voltage, although bus 10 does not connect the plant serving as the oscillation source, it has the largest oscillation magnitude. So what does this tell us? So this tells us that when we try to look for the bad actor in one oscillation event, we should not only focus on the oscillation magnitude and just based on which bus has a larger oscillation magnitude, then the plant connecting to which bus is the bad actor. And for this specific example, if we further dive into it, we will see that bus 10 actually connecting to some switched shunts, some fixed capacitor there. We know that a capacitor is good to provide some reactive power, but it is bad since its output is related to the voltage level. If voltage level goes higher, we don't need so much reactive power. It provides more reactive power. When the voltage is lower, we need a lot of reactive power. The capacity provides less reactive power. And this is probably why. So bus 10 has the largest oscillation magnitude. And in other words, there is some resonance here. Bus 10 is not the source of the oscillation, but bus 10 creates some resonance to amplify the oscillations here. And after knowing that the oscillation source, so we can come up with some oscillation magnitude method, mitigation method. So the first one is very brutal. So we know that plant 1, plant 2, they are the oscillation source. So what we did is assume that we see the oscillation in the simulation, and then we immediately disconnect one of the major oscillation source. So here what we did is we disconnect plant 1. So at this 10 seconds, so what we can see is that in the green region without the major oscillation source, without one major oscillation source, the oscillation basically disappear in both the voltage and the frequency waveform, which shows that this seems to be effective. And there could also be some other mitigation method. For example, a major one is if we do some short circuit current calculation, we will confirm that this is a weaker grade region. And for example, if we check the short circuit ratio at this plant 1 bars, we will see a short circuit ratio SCR between 2 and 3, which means that this is a weak grade connection. And so our mitigation method 2 is to basically to strengthen the grid. So here what we did is we simply add one transmission line around this region to strengthen the connection between these renewables and the main grid on the upper part. And here is our simulation results. We can see that following the disturbance, following the fault, and after cleaning the fault, we see basically no oscillations here. So it shows that strengthening the grid is one effective method to remove the oscillation to improve the stability. And that's system A in year, basically 3 years ago in year 2021. And we further see the system is keeping evolving, like the system around the world. Different systems set the goal to achieve renewable penetration by which percent by 2030, by 2050. And this system A is also keeping evolving. And the major changes are there are some new renewable plant and which probably exacerbates the system stability, but also there are some topology changes. We have some new lines, and we also have some old lines retired, and there are some change in the protection setting, basically to relax the protection and to reduce the chance of trip this line and isolate this region. And so now so our question here is we are interested in currently, so the current system, is it become more stable or less stable? So here we consider two cases. One case is corresponding to some low renewable output, and case 2 is corresponding to some high renewable output. And also we consider different fault locations. But first, let's still consider the original fault location here near bus 1. Now here is our simulation results. Recall that we have a low renewable output case, which give us a stable result. And we also have a high renewable output case, which also give us stable results. And this give us the impression that although we have new renewables, and the evolving system is actually becoming more stable due to the topology change. And it's not going unstable, like it's a little bit counterintuitive. And this case is stable, so if we have a fault at the original location, but N-1 could occur in different places, at different places. So here we further consider another fault at this bus 3. And this fault is a little bit more serious because this fault is at a higher voltage level, and it is closer to the main grid, which is supporting the voltage. And again, we consider two cases, and the only difference is for the location. Here is the simulation results that we get. So on the left-hand side, so if we have a lower renewable output, we can see that we have some oscillation, but they are still be damped after a while. But if we have a high renewable output, we see these oscillatory results in the IM simulation. So this gives us the conclusion that high renewable output makes the system more stressed and basically increases the chance of being unstable, and also afford closer to the main grid, closer to the main part of the grid, basically introduce higher risk of instability. And here, to solve this issue, indeed, we can explore different options. For example, to install some StatCom to further strengthen the grid. But we know that if we install some StatCom, we need to do some further study to select the capacity, to say like where to site the fax device. Here we have some concluding remarks for this specific event. So the first is the oscillation source. And the oscillation source here is some IBRs. Specifically, there are some wind farms there, and they are operating on we call it some highly stressed conditions. Basically means that it is connected to some weak grid. It has some high renewable output. And the second remark is that so when we are trying to identify which is the bad actor in the oscillation event, also the oscillation source. So we should not only care about the oscillation magnitude and pick up the bad actors based on the oscillation magnitude. We need some more algorithm like the DF or some other method to help us identify who is bad actors there. And also, we care a lot when we are doing analysis. We care a lot about the mitigation method. So we know what is the bad actor, how to address this oscillation event to prevent our system from this event, similar events in the future. So we try two simple ways. One is simply disconnect the oscillation source. So after doing some study, we know which is a bad actor and simply disconnecting them. And the second is basically to strengthen the grid and keep the system away from all these issues. And we also know that like, we need to keep doing the study. So the system is evolving with topology change, with new different generation mix, and it's possible the system become more stable as here. It's also possible with more renewables, the system is less stable. And we should be especially aware of the high renewable out case, and there are some if there's some critical manifold contingency closer to the main grid. And also we can also consider like some fax device, or like we convert some existing super generator to the StatCom to some synchronous condenser. And here let's do some comparison. All our studies based on the phasor domain studies, and we know that we can also do EMT studies. So let's see why comparison with another example we conducted in another DOE CETO funded project called SciFi, and we collaborate closely with KIUC, Kauai Islands Utility. And the first is the possibility. So in our example we just shown, so we use phasor domain simulation to recreate the event. But in this in another event, so which is an 18 to 20 Hertz oscillation event in Kauai Island, as we shown here. So if we do phasor domain studies, we get the red trace. The blue trace is field data. So basically, we cannot recreate that event, although we can recreate this event here in system A. And to recreate that event, we need some detailed EMT study. So first key point. So sometimes phasor domain simulation can give us the event replay, sometimes not. And the second key point is highlight the importance of the field data. So our analysis here is purely simulation based. We don't use the field data. But if we have the field data, we can directly know the oscillation source. We can do different analysis like mode shape comparison. We can do some analysis to confirm which our simulation is. We get some simulated oscillations to help us. The field data can help us confirm. So our simulated oscillations are the actual one. And the third key point is we didn't try to to mitigate the oscillation with grid forming control. But in that event in Hawaii Island, we are able to mitigate the oscillation with grid forming control. But that grid forming control is adopted in battery devices. Here, so in this system A, we started. So most generations are wind there. So yeah, so we might need to consider like, should we basically adopt grid forming control in these renewable plants directly? And that's basically some further thinking, like based on to compare this study with some previous studies that we have. Finally, we would like to highlight the importance of the vendor-specific model. So there are so many characteristics, and sometimes the generic model cannot capture. So it's very important to have the vendor-specific model if possible. Yeah, that's basically my study, and I would like to hand it back to Barbara.
Thanks, Xuan. Great presentation. Thanks for staying on time. We're perfectly on time. That never happens. Okay, we're going to go ahead and take some questions. And thanks, Nick, for answering some of them already. Let's take one from Abdulaziz Saidi. So many studies are focused only to the low frequency, for example, less than 60 hertz. But with the increased penetration of HVDC and IBRs, et cetera, we should have a small signal model for the high frequency oscillation. So his question is how to model it. Is there any software capable to do the small signal stability for high oscillation greater than the fundamental frequency? And I push that to either of you.
Let me start, and then I'll defer to Xuan, who's living that world day to day. Yeah, there's an emerging variety of tools out there that are suitable for these higher frequency phenomena, and you got to be a little careful. You know, when you say high frequency, there are lots of IBR driven things starting to materialize, and NREL's got good examples that are above 5 hertz. And when I say 5 hertz, that's 5 hertz modulation of fundamental, and you got to be a little careful if they're added. And I don't need to go there, but so phasor domain analysis starts to fall apart somewhere around 5 hertz. You can no longer have algebraic positive sequence representation, and you need to go to other tools. There's a growing body of tools out there that are either EMT based, that are designed to extract frequency domain, like these dynamic frequency scans, from good fidelity EMT models, or hardware in the loop, control hardware in the loop. So RTDS type things where you can extract small signal models from the real equipment. So there's a bunch of different tools. And as not to push the guide on you, but there's a page or two of discussion, hopefully not overwhelming, in the guide that sort of talks about the different, sorry for lack of a better word, flavors of these tools. Xuan, you want to add to that? Because you guys have been doing great stuff.
Thank you, Nick. Yeah. As Nick mentioned, so we have some low frequency oscillation, and that the IMS tool could capture. So many IMS tool basically have the small signal analysis blocks there. We can just use that for some high frequency oscillation. So as one page of Nick's slide summarize, there are different methods like state space based conventional eigenvalue analysis or some frequency starting. So currently we have for the state space based analysis. So our collaborator in Purdue University actually are developing some tools, and also there are some other commercial tools there. And this is also true for the frequency scanning method. There are commercial tools there, and there are some open source tools there. But like they are very precise and give us a lot of insights, but sometimes they are very computational intensive. Basically, the results is very insightful. Yeah, we need to take more efforts to just get the results.
Great, thank you guys. Okay, let's go with how is the IBR modeled in the sequence model during the fault studies, and how does the IBR contribute to the fault studies? I know that's sort of a broad question, but if you can address it somehow.
Again, I can start and then I'll Siobhan and I will do tag team. Well, I guess first of all, the seminar today is on oscillations. These different modeling questions do have overlap. Generally speaking, for oscillatory type problems, we are usually not worried too much about the equipment being driven hard into various limits that are associated with fault conditions. So I'm answering your question a little bit obliquely. The big deal with fault modeling, including sequence models, so things like Aspen, is getting the behavior of the IBR when it's in limits right. And there's a very rich body of research and published results out there. Having said that, ISOs and utility people all over the world are still wrestling with this. It's not an easy answer. The only thing I will say that's encouraging is that the emerging classes of IBRs, particularly ones that are grid forming, are actually a little simpler to model and fault behavior. I understand it's not a terribly satisfactory answer, but maybe Siobhan can add some flesh to it.
Yes, Nick. So if the question is for our studies that we just discussed, so we use some generic models that are available in that software. For example, the wind farm, so we have some WT3G1, WT3E1, and more broadly, as Nick mentioned, so the generic model. So one critical issue is we hit the limit. We have some fault behaviors, and this is something that should be aware of. And there are many ongoing efforts. For example, the Unify project is developing different grid forming model, GFMA1, GFMB1, like to represent the behaviors for these IBRs. So, and also there are some existing generic grid following models here. So basically, there are a lot of existing works and a lot of existing studies here, and these models are being integrated to the commercially available software or some open source tools now. Yeah, we are working on this. Yeah.
Thank you. Okay, another question we have. Okay, and this is for Siobhan. While you've identified the main culprit, one wind farm out of 5 in this main case study, it remains unclear what the proposed mechanism for the creation of the oscillatory event is and how that relates to the specifics of that particular wind farm and its inverters.
Yeah. Thank you. It's a great question. So, yes. So if the question is let us to share the root cause. So currently our identified root cause, we call it a highly stressed operating condition, basically a combination of high renewable output together with a weak grid. But as you mentioned, so you would see that we didn't find a nice parameter tuning method to remove the oscillation. So parameter tuning is basically the cheapest solution. So if we hopefully understand the mechanism, and we can do that. But here, like so because one reason that we didn't find this very specific root cause is from the modeling issue that we have just discussed. So we use some generic model. Actually, when we are trying to use the vendor-specific model, so we see some issues. So the simulation crash. So we tend to use the generic model. But as you will see, like the generic model is less representative than the vendor-provided models. That's probably one major reason that we get a higher level root cause, but we didn't get a very specific root cause for this case.
Thank you.
Sorry. Well, I just want to add a little color and maybe talk about some of the work I'm doing now, research. But the question of this root cause, there's some work that I'm involved with right now that is set on trying to, in some sense, simplify this question of stress that Xuan correctly pointed in. And I should the little example in my talk, right, where the loading goes up, 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 right? So the system strength, as a short circuit strength, isn't actually changing in that particular example that my charts showed. That was an example from Professor Fan at South Florida. But at a certain level of system stress, the system goes unstable. And there's some encouraging work that I'm involved with that sort of that captures the cross section of sort of short circuit strength and loading stress, and says, without going into great detail about the control algorithms of the IBRs, hey, this is very ill. The system is very ill posed at this strength and this loading. So we're hoping from that to be able to create some understanding and hopefully some operating tools that give system operators a little better warning that says, look, this is, without huge amount of information, this is, you're starting to get into the red zone, or the warning zone, where the system is so ill positioned that you're running risks of stability problems. And then the idea is that hopefully can cover a variety, not just oscillatory stability, but sort of first swing stability and other kinds of problems. So the industry is still on a learning curve. We're getting smarter about sort of recognizing these problematic operating conditions where you've taken the system a step too far. So there's some good stuff out there. Stay tuned. I think the next few years will put a bunch more practical tools in your hands. Okay.
Yeah, that's a good point. So guys, it is after 9 o'clock, or 9 o'clock in Denver here. If you need to drop. We're going to actually go a little bit long, like another 5-10 minutes at the most, to get some of these questions answered. We really appreciate all the participation. So what threshold of oscillation, for example, 5%, 10%, something higher, warrants attention? So, or should any level of oscillation be addressed? And is that related to specific grid codes? Like what levels sort of become problematic? Is there a general rule of thumb?
Yeah, let me do that one too, and then sorry, Xuan,
No,
I keep
yeah,
jumping
go
in front of
ahead.
you, but that's a great question, and one that was of considerable interest or concern to many of the participating authors, contributors to the guide. What do you do? So I'll give the short answer is that it is imprudent. So this is Nick speaking, but this is what it says in the guide. It is imprudent to ignore an oscillation that you do not understand. All right. So even a relatively small oscillation, small amplitude, can be to use could be a warning of a risk. So for example, a small sustained torsional oscillation is something to be worried about, because it may mean that you might be very close to an instability that could have severe consequences. Other kinds of small oscillations, once you understand them, sometimes can be ignored. You have for example, a deadband on a voltage controller that occasionally will sit there and dither. Once you've figured it out, you say, no, okay, I understand that this is a characteristic of this controller. The oscillation isn't big enough to damage any equipment, to upset customers. Yeah, I can ignore it. So that's the philosophy forwarded in the discussion of, do we need to fix it, in the guide. Got to understand what it is, then consider the risks and consequences of the do nothing option. And the do nothing option is absolutely legitimate if the risks are acceptable. Okay.
Yeah. I would have to echo with Nick. Sometimes we see some small magnitude oscillation. We might need some magnifier to find it. But on the certain condition, it's possible that could be very large suddenly following some M-1. And back to the question, I think the question is asking if we have such a magic number, a critical renewable penetration level, or some critical IBR penetration level there, such that we reach that level, we know that we have the risk. But unfortunately, like our current study shows that looks like no. So the critical IBR penetration level is very system specific. And I work together with one colleague at University Tennessee, Zhenping, and we find that many different factors like the IBR locations, the topology, the grid conditions, the parameter tuning, they all affect the condition above which we would create the oscillation. For example, for the same grid following inverter, if we add some PF droop control, so maybe the IBR would lose stability and be oscillatory after the short circuit ratio is about 3. But if we remove that PF droop control, it's possible that the IBR is stable when the short circuit ratio is around 1. So it's very system specific, and unfortunately, we believe we don't have that magic number. Specific analysis needed for specific system. Yeah.
Thank you, Xuan. Xuan, can you elaborate on how to determine the optimal location for the StatCom that would help mitigate the instability with the fault located closer to the main grid if it wasn't so far?
Yeah, this is a great question. So I can share my thoughts. So what we did in the simulation, so actually we didn't find the didn't spend effort to find the optimal location and optimal capacity for system A. And one method is very brutal, like we just do a bunch of simulation by placing the model, the StatCom model everywhere and do the n-1 contingency. And that's very brutal, but very practical. And the second one, I didn't try just an idea. I believe is that we can check the grid strength everywhere in the system, and we pick some weak point closer to the renewables. And yeah, that's another idea, but it's just some idea. Like I haven't tried it yet.
Thank you. So, okay, this is sort of a more general question for both of you. So how do you view the impact of grid forming converters compared to grid following converters on these oscillations?
Yeah, would you like to go ahead, Nick?
Yeah, I'll go ahead. They're different, huh? It's the quick answer. So there, and I saw somebody ask something about virtual synchronous machine versus droop oscillators, and that that choice of control can also make a difference. In many regards, we're finding that that grid forming algorithms tend to be a little better behaved. That is, the system could take a little higher stress, more transfer, whatever, with grid forming than they can with grid following. Got to be really careful about too many generalizations. Some of the control algorithms, for example, virtual synchronous machine, it is possible to make a virtual synchronous an IBR look sort of indistinguishable from a synchronous machine. Well, synchronous machines have oscillatory stability issues that we've known about as an industry for decades that require power system stabilizers. So one has to be a little careful. Do not make the mistake of thinking that the closer you get to a synchronous machine, the better things are. That's simply not true. And the industry researchers like Xuan are constantly working on trying to figure out the best way to go forward, not, says Nick with great emphasis, not how to repeat the old all synchronous system. Do not make that mistake. That's not the future. So there's a lot of opportunity out there for us to do better, and GFM is almost certainly a part of that solution.
Great, thanks, Nick. I'm going to just keep jumping through, so hopefully we can answer the balance of the questions here. So the phasor model used for the studies are positive sequence-based, but the fault study was unsymmetrical still. So how are you able to capture that low frequency oscillation successfully?
Yes, this is a great question. So actually, we have the fault there, but I believe the fault in that specific study, the fault itself. So just to since the fault is quickly cleared after 250 milliseconds, so I believe like in that specific data study, so the fault itself just reduce the grid strength since we clean the fault by removing some lines and just triggers the oscillation. So in that specific design, so the fault didn't affect the behavior of the IBRs so much. So just focus on the post-disturbance IBR behaviors. But this is a great question. So especially for the study of the IBR modeling. So when we have some fault there and we are care about the for example fault right through behavior or some behavior IBR performance on the unbalanced conditions. So I will see that in our specific study, we didn't put a special focus, just use the generic model. But this is a great question if we really care about the IBR performance under the fault conditions, yeah, when the fault is still there. Hopefully this can answer the question.
Thank you. And what are the simulation tools that are helpful to study oscillations generally? I think we can just do a little laundry list.
Oh, yes, this is good. So I think this question requires some name of the software.
That's fine.
So for the low frequency study, so we use PSSE. So this is only 1.5 hertz. So we still get the chance to capture the oscillation. So as Nick mentioned, so we might have some number like 5 hertz here. But for the Kawaii study, so we try PSSE, but we didn't capture it. Even we get the vendor's models there, we plug it into the PSSE model from the system. We didn't do any network reduction. So we are not able to get the oscillation, so around 20 hertz. So what we did, like we moved to EMT software like PSCAD, and we collect the vendor's model, and we are able to recreate the event. But also like one problem is that I believe one problem when we are doing study, what problem is when we get the vendor's model, we need to examine the model and we need to check the model if actually. So for example, these are some parameter tuning in the plant, and when the system operator is operating the plant, maybe they can do some change online, like the droop constant or some other parameter. So the parameter is changing, and it may not match the parameter tuning in the vendor specific model that we get. So we need to check like they have the matching like parameter settings. Of course, there are some parameters it's difficult to check, but at least like what we can access to make them match and then do the starting.
Great. Have you guys noticed any oscillations occurring on the distribution system, like below 60 kV, something like that? Are you seeing that?
So it's a great question. So I'm not aware of that, and one reason in my mind is so as we mentioned, so we find one conclusion. So for example, in the distribution grid, for example, for the PV, we use grid following control with a fixed P and Q control, and there's no grid supporting feature like the PF droop control. And our study shows that if we have that advanced grid supporting feature, it will reduce the stability. But for this PV at the distribution level, since it's only fixed P and Q control, and it has the increased stability basically.
Okay,
Yeah,
one final. You want to go ahead, Nick?
no, Xuan's answer is sufficient. That's good.
All right,
Go ahead.
we're going to do one more and then wrap. Okay, so have the grid codes evolved sufficiently for weaker grids? So in other words, are the control and performance demands on the IBRs, are the current grid codes pushing them in an unstable direction? Like, do we need to sort of rework grid codes to address this?
I'll make a quick answer. I think we still have some work to do. The current grid codes are getting better, and of course that's a broad question because we have a very international audience here. So the grid codes aren't monolithic. Some of the performance pieces of the grid code, and I think I get where that question is coming from, are very prescriptive in terms of asking for very aggressive response, very fast response. And the grid codes that don't make allowance for the for, you know, in some sense, abrogation or there's another word for it that I'm slipping my mind, to account for the reality of the particular application, of which weak grid is frequently the key element, where you reduce the aggressiveness of the control for credible operating conditions, really can get you in trouble. So yeah, we're getting there, but there's a big warning mark on prescriptive grid codes that don't have allowance for situational variance.
Yeah, I agree with Nick. So if we have some strong grid, so maybe it's fine to require some faster response, since it's a strong grid to support everything, and how a faster response can basically help the system have better dynamics. But for weaker grid, so if we have the requirement to require some, for example, some response within 30 time limits, so it's well intentioned, but it reduces the stability of the plant itself. So yeah, so some trade-off is there, and as Nick mentioned, we are improving now. Yeah.
Great. Okay, I think that's all. And I thank you both so much for your wonderful presentations and staying long to answer all the questions. And thanks everybody for attending. Please do fill out the survey when you get it, and we will make these slides and the recording available. So thanks, and everyone have a really wonderful holiday season. Hopefully you don't have to work for too many days beyond today. Have a break, relax, drink some eggnog. Take care.
Okay.
Thanks,
Cheers, everybody.
everyone.
Thanks for hanging in there.